So hi everyone, welcome to the exam 3 review session. So I am Ashley, one of the pilot leaders here, and then we also have Maggie, Kristen, and Jose with us today, all who are helping out with the review session. So just when we're talking or if someone else is asking a question, please just have yourself muted. And then also if you do have a question, or want to participate in any way, please just try raising your hand unless the speaker is saying like you can shout out. And then I am recording this so that I can post it to YouTube later and then share it with all the people who either want to rewatch it or can't make it to the session. And I guess one other thing is that we may or may not be able to get into the NMR, like spectroscopy type stuff, depending on time. And if we don't, we do have a video prepared for you guys with slides just in case that does happen. So yeah, other than that, I think we are good to go. I'm gonna try connecting my iPad and sharing this with you guys. Are you guys all able to see this? Oh my gosh, where did you guys go actually? I cannot see you.
It's still black for me.
Oh my gosh. Let's try this one more time. Sorry.
It's still black. I don't know if there's a lag with your iPad.
Are you, damn, okay. Let me just try joining from my iPad then, because I was trying to AirPlay it. Sorry guys.
Do you just want me to start from 17 in case your iPad's like bugging?
I think I can join, just give me 1 minute. I'm sorry. I'm so sorry. Thank you, Kristen. I appreciate you.
You're good.
It really never works for me either, so.
It's good.
Okay, perfect. Yay. Sorry, I just needed to give myself that moment. Okay, anyway, now, so we are in review session 3, last exam, yay, almost done with Oracle 1. So just as a disclaimer, as always, yes, we are your pilot leaders. We have gone through Orgo, but we are not involved in the overall administration of your course or how Dr. Tovar wants to specifically teach it. So in case we do say something that differs from Dr. Tovar, we did take it from different professors. So we might be saying something that's slightly different. So just if he contradicts us or we contradict him, always follow what he says, because he is the professor and knows best. Alrighty. So to start off, we wanted to go based off of your syllabus in order of what you guys will be tested on. So we're starting with benzene. So it is one of your aromatic compounds. It's a very stable compound and it ends up looking like this. So
can you get back to my AirPods? It doesn't work.
Put them back in the case and then take them out again.
Who's ever talking, could you try muting yourself, please? Thank you. So we have our 6-member ring and it's fully conjugated where you see that it has your 3 double bonds, and then it's very stable because it can resonate. So you are able to arrow push the double bonds all around and you're able to get this new structure. I'm sorry if my drawings are ugly. And so having that resonance and a ability to delocalize all the electrons where you end up getting this hybrid makes it very stable. And just in terms of trying to show you guys that I can draw out the orbitals. So here's your 6-membered ring. And then remember that these are your sp2 carbons. So you'll have, I'll make sp2 orange. So off of this carbon, you'll have an sp2 orbital, another sp2, and you should have another sp2. I'll draw up your hydrogens as well. So this happens on all of your carbons. Sorry, my orbitals are getting uglier and uglier. But those are your sp2 orbitals. So you have 3 sp2 hybridized orbitals. And then on these carbons, you also have your p orbitals that are regular and unhybridized. And all of these orbitals interact with each other, the purple ones, the p ones, where they're able to delocalize your electrons throughout the ring, which ends up making it more stable. So just to write that down in case you guys want to write it down for notes, your pi electrons are delocalized across the entire ring. Making it stable. Now, when I was describing this molecule, you guys might have been confused and said, what is an aromatic compound? Or if you were watching all of your lectures, you will know what an aromatic compound is. So in order to have aromaticity or for a molecule to be aromatic, you need 4 requirements. Those requirements include that it's cyclic, it's fully conjugated, it's planar, and has an odd number pair of pi electrons. And so just to go into what each one means, number 1 for it being cyclic means that the molecule has to be connected, where it's like a triangle, a square, a pentagon, or a hexagon, or getting even larger and more difficult to draw, or or larger and more difficult to draw. It's not something that's just connected in a straight line. For fully conjugated, that means that all of your carbons are sp2 hybridized, because they can be stabilized by that pi orbital interaction. And then this means that you don't have any sp3s. And then in terms of your molecule being planar, that means that your molecule lies all in the same plane. So that means that if you have something that's cyclic, it's not going to have something that might be going like a methyl going down and then a methyl coming up. It's all going to be in one plane instead. And then for the last part, the molecule must have an odd number of pi electron pairs. That means that when you're counting off of a molecule like benzene, which is aromatic, you have your 3 pi electron pairs. So then 3 is an odd number and it's happy. So you have full aromaticity, because if you look in this molecule, it is cyclic, it is fully conjugated, it is planar, and it has an odd number of pi electron pairs. This idea of an odd number of pi electron pairs also goes into the idea of having Huckel's rule, which is the 4n plus 2. And one thing about Huckel's rule is that n is not a characteristic of the molecule. So that means that when you're looking at your molecule, you're not going to be like counting things off of it like I just did with that odd number of pi electron pairs. Instead, you're looking at how many electrons it has and trying to get it equal to a number. So if you had something where n equals 0, then you would have 2 electrons. If you had n equals 1, then you would have 6. It goes up to like 10 and then 14 and then 18 if my mental math is working correctly. So in this case, when you have benzene here, you would have 6 electrons, pi electrons. And this goes hand in hand because we're looking at pairs when you're looking at the odd number, so it's 3. But if you're looking at just the electrons alone, it's going to be double the amount of the pair. I personally like using the odd number of pi electron pairs and just counting, but if you prefer using Huckel's rule with the equation, go for it. Now, let's go over some examples of aromatic rings. So the first one that you can have, that was not drawn well, is if you have a 3-membered ring, and if you have something with a double bond there and a plus sign, that could be an aromatic ring because it is cyclic, it is fully conjugated because all of them are sp2 because of that positive charge, and then you have it all being planar, and it has 1 pi electron pair, which is odd. For another example, you can have something like maybe like this, where it also has a triangle shape, but then you had boron attached to it with a hydrogen, because this will also be cyclic. It still is fully conjugated, because boron is one of your unique atoms, and then it is still planar. And then it still has your odd number of pi electron pairs. And then I guess another example could be if you had a 5-membered ring, and then you have a lone pair off of it with double bonds there, because this becomes sp2, and then all the others are sp2, so then it still is cyclic. It still is fully conjugated. It still is planar. And it still has an odd number of pi electron pairs. Now, does anyone know how many electron pairs it has? Feel free to shout out. 3, perfect. Yes, so you have 3 here because you have 1, 2, and 3. So 3 pi electron pairs. You also have another example that you can have is if you have a 6-membered ring with nitrogen. Just have to connect that with your double bonds, because it still is cyclic. It still is fully conjugated. It still is planar. And then you still get an odd number of pi electron pairs. Now you're going to count and see 1, 2, 3. So you still get 3 pi electron pairs. Does anyone know why the electrons off of nitrogen are not counted in the pi electron pairs?
Is it because they're part of the sp2?
Yes, that's perfect. So the idea behind this electron pair is that they don't participate in your pi system, because if you were to look at your ring, you would have all of your p orbitals that are interacting with each other like I drew before. But then the lone pair off of nitrogen is participating in one of those hybridized p orbitals that we were talking about before. So it's not going to delocalize itself and participate in the resonance structure. Does that make sense for everyone? Okay, perfect. Now, these are examples of aromatic rings, but then you can also have something called anti-aromaticity or an anti-aromatic compound. Oh, I did not write anti. And so the rule requirements for being anti-aromatic is also very similar, where it needs to have the first three are the same, where it's cyclic, fully conjugated, and planar. But the last part is where it differs, where you have an even number of pi electron pairs. And then in terms of Huckel's rule, I believe that it turns into 4n. And then so to go over some examples of anti-aromaticity. One example from kind of similar to one of the ones I drew before is if you put a positive on a 5-membered ring, and then it still is cyclic. It still is fully conjugated. It still is planar. But then now it has only 2 pi electron pairs, so 1, 2. And then another one could be if you have like a 4-membered ring and you had double bonds there. So it's still cyclic, fully conjugated, and then it still is planar. And it still has 2 pi electron pairs with this double bond there and this double bond there. And so, yeah, I think, oh, one other thing that I forgot to say about anti-aromaticity is that it's very unstable. So your aromatic compounds are going to be very, very stable. And then your anti-aromatic ones are going to be very unstable. And then I think that's about it with that. So, and beyond your aromatic and your anti-aromatic compounds, you also have compounds that are just going to be neither of them. And this can include a couple reasons why a compound won't fit it. One example is if it's not fully conjugated. So it can be kind of like that 5-membered ring that we just drew. If you have the double bonds, just like before, if we're looking back at it, it's still cyclic, planar, and has 2 pi electron pairs, but it's no longer fully conjugated at this point, because this is now sp3. Before, having that positive charge there made it sp2, if that makes sense. One other way that it can no longer be aromatic or anti-aromatic is if it's not cyclic. So if you have something where it is still fully conjugated, but it's not connected in a cyclic molecule, then it will be neither aromatic or anti-aromatic. Another example is if you have something that's non-planar. So a molecule like this can be, is if when you get to bigger rings, you will have it's going to be less likely to be planar. So past a 6-membered ring, there is a high chance that it's going to be non-planar. Obviously, this is not absolute. There are molecules that are past 6-membered rings, but they will not always be fully planar. If you look at molecules that are smaller than 6-membered rings, then it's a lot harder to tell. And so just because I drew this molecule out planar does not mean that it actually is planar, because if you were to draw out what it would look like in its chair conformation, it would look something more like this. If I can actually draw it, it's a little difficult and I am not the best artist. I'm not gonna lie to you guys. Where the wings come off. This is 1, 2, 1, 3, 4, 5, 6, 7, and then your 8 should be down here. So it's going to look more kind of like one of those boats that we were talking about, where it comes up on both sides during chair conformation. So that's how you know that it's non-planar. Does anyone have any questions that they want to shout out before I move on past aromatic, non-aromatic, and anti-aromatic compounds? I can take like 1 or 2. No.
I have a
Okay.
question. So Tovar talked about like the 2 aromatics joined together, and then how when you have like a resonance form, there's like a plus charge in one ring and a negative charge in another ring. So like, how does that work again?
So if you have like 2 molecules joined together,
Like 2 aromatic rings together, and then like you have like a resonance form.
oh, I think I have seen something like this. I've never actually done a reaction on it personally, but I have seen where they have overlap between some of them, where after the reaction they kind of overlap like that. Then like it would have your 6-member ring. Well, where it would look a little more like that. And then because like these, I think areas overlap, and then you have the 2 6-membered rings, it would no longer be planar. I'm not fully certain though on the whole logistics of having those 2 rings interact, but I have seen examples of that. One other question. Oh, sorry. I got a message in the chat for, can you do the 4n plus 2 example for a molecule? So personally, I don't use the 4n plus 2 as much, but then if you were to use it, so on something like benzene, in terms of your pi electron pairs, here you have your p orbitals. Each of them has 1 electron, so 1, 2, 3, 4, 5, 6. You have 6 pi electrons, and then for 4n plus 2, 4n plus 2 is equal to 6, and then you get that n equals 1. And so the 4n plus 2 with Huckel's rule is that you need n to equal an integer. So since 1 is an integer, then it's okay. Yeah, and so like any examples of them can also be where n equals 0 and it's 2, n equals 6, n equals 10, n equals 14, and n equals 18. And then we can try looking over here. Which one should we do? We can try looking at this one. So you have 1, 2. So here's where you have your p orbitals. And so then it's just 1 and 2. And so I think that's an example where 4n plus 2 equals 2, so then n equals 0, because there's not an electron there in the p orbital. And then you can also do it for the other molecules. So if we were to do it with the one that we have with the molecule that I drew out up here, you have 1, 2, 3, 4, 5, 6 p orbitals with electrons. So then 6 equals 4n plus 2, n equals 1. So then you're happy that it's an integer. And then you know that it's aromatic, but then for the 3, and then it also matches the idea of doing the odd number where 6 matches with 3, because you're looking at pairs versus just single electrons. Perfect. Alrighty. If anyone does have any other questions, I'm not trying to skip you, but please ask them in the chat because we have other leaders that can answer them. Alrighty. So now let's move on to Diels-Alder. I know that you guys covered it, I think, right before Thanksgiving break, or right before one of your exams, and then a lot of my students forgot about it, and it made me very sad. But Diels-Alder is a very useful reaction, especially in terms of doing synthesis problems. It's a pericyclic reaction. And so what does pericyclic mean? That means where you get the electrons to flow in a cyclic manner. Or mechanism. And so Diels-Alder has 3 main components when you're doing it. You have your diene, which has 2 conjugated double bonds. You have your dienophile. D-I-E-N-E-O-P-I-L-E, yes, which is 1 double bond. And then you have heat. You need heat in order for the reaction to occur because this reaction will not occur at low temperatures. And so when you're looking at your mechanism, you are going to have to rotate this from the S trans to the S cis, the conformation. And so it will look like this when it's in its S cis conformation, and then you'll have your dienophile. And so when it reacts, I always like drawing these dotted lines in between your diene and your dienophile. And then when I push my arrows, I push this part of the double bond, one of them, onto the formation of a new bond, single bond. I move this one, resonate it over, then I push this one there, which forms a new single bond as well. And so this ends up forming your molecule with its double bond, which is now a cyclohexene. And so just in order to color code, so that you guys can better see where these bonds are going, this double bond will move here. This double bond is moving here, and this double bond is moving up here. And just, it also conserves the amount of carbons that you have. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this reaction is not adding any carbons. It's just making a ring. And so now some of you guys might be asking, why does it have to be S cis? Excuse me, instead of S trans? So in your S trans, if you were to have your diene here, these, if you were to number it where it's 1, 2, 3, 4, the 2 ends that are interacting with the actual mechanism, 1 and 4, are too far away from each other to actually simultaneously react. Instead, you have to have it in your S cis conformation, where you can have 1, 2, 3, 4, where you can have 1 and 4 simultaneously interact with that dienophile. And then that's how it's able to form the ring. Alrighty. Now with Diels-Alder, one other aspect of Diels-Alder is that you can influence it with the addition of electron donating groups or electron withdrawing groups. And this is a method of influencing its reaction rate to make it go faster. So if you were to add an electron donating group to your diene or an electron withdrawing group to your dienophile, that would increase its reaction rate. So some examples of this is if for your electron donating group on your diene, you can do something like OME, because then you have 2 electrons, or actually you would have 4 electrons, but one of the pair of electrons can resonate down, and then you can resonate the other parts of, you can resonate your other parts of your molecule into the rest of it. So then the electron donating group here is donating electron density with resonance. One other way is that you can have an induction effect with a methyl group added on top, where there are differences in electronegativity causing it to donate electron density into the rest of the diene. And then for electron withdrawing groups, you can have resonance again with a group that withdraws. So if you were to have on your dienophile, if you were to have something like, I guess, a carbonyl group off of it, you can have it where it would resonate and it would draw electron density out of the diene, which is in this part. And this is via resonance. And then one other way for it to happen with an electron withdrawing group is if you have induction. So you can have something like this. Oh, actually, see, and then if you had like CF3 off of your diene or dienophile, you would have it where F, and then the electron density would be going out into those F atoms, which would be pulling it because it's very highly electronegative. And then when looking at your electron donating and withdrawing groups, I do recommend looking back at one of your old pilot sets because we did cover partial charges of these groups and how they should interact, which should be lined up in order for a more favorable reaction to occur. And I think this was in one of the earlier problem sets, maybe like 9 or 10. Alrighty. And then Diels-Alder can also happen on bicyclic rings, or happen with bicyclic rings where they form it. Here you still have it in your S-cis conformation, and it's locked in because it's in a ring. So since it's S-cis, we are still happy. And when you're doing this reaction, just so that you guys can see how it forms this, it ends up looking where, actually, I'll draw it based off of the molecule here. So I'll draw my dotted lines. You can have it where these electrons are moved. And then just so that I can color code everything, you'll have pink, or you'll have orange, and then these would interact to here and here. You'll have your green matching up with this new bond, and your, let's make this blue, matching up with the formation of this bond. And then what else should I color code? I can make this pink and then this corresponds to that. But if it does help you see the molecule better, it will form a 6-membered ring where you have a cyclohexane as its base, and the pink will still be there. And then you'll still have the blue forming this bond and the green forming this bond, just like normal. And then the one part that makes it a little harder to see is that this orange part of the ring will pop up. So it's going to come up as if it were wedged here. And then you have just a bond connecting the two of them. And so that's what this part is showing, where you have the orange part coming up. So both of them, you're going to have basically 2 rings off of each other. And then for the bottom one, if we were to do its reaction, you would have, actually, you kind of need to rotate it. So let me redraw it out. So if you have it on the side, you would have your electrons moving this way. And then it would end up forming a 6-membered ring, just like normal. You would have your double bond there. So this corresponds to the blue moving there. And then the pink here corresponds to this bond forming. And then the green here corresponds to this bond forming. But then you still have this purple part of the molecule. And so it's going to pop up. So you'll have a wedge part here meeting another wedge part here. And so it's going to create this center where I'll make it in orange, kind of like a point, which shows up on that molecule. Alrighty. And then one other way that Diels-Alder can also show up is when it's on alkynes. So you can have our diene kind of like before in the S-cis conformation, but then you can have your dienophile be a alkyne, which is your triple bond. So if you were to do something like this, do your dashes, this bond is going to move up, this bond will move down, this bond will move down, and then this will form a 6-membered ring like normal. And just a color code where you guys see things are moving. You have the orange moving there, you have your blue. Actually, ooh, oh no, I did not draw the hexane. There we go. Then you have your double bond there, and then you have the pink moving here. But one part is that your green will stay here, but then you will have a double bond there. So having Diels-Alder on an alkyne will leave a double bond on the opposite side as well. And you can also do, yes, this also still involves heat. You can also still do this if it has substituents off of the triple bond. So if you had something where it was a diene here, and then you had a triple bond with like groups like this off of it, these would interact so that it would form the same cyclohexene, but then you would have these coming off on top and on bottom. And just to explain how I know where to put those substituents, if we were to draw out the mechanism, you have this moving up, this moving down, this moving down. But then let's number our number our carbons. You have 1, 2, 3, 4, 5, 6. So off of your ring, you're going to go 1, 2, 3, 4, 5, 6. And so you know off of your 5th carbon, you have this group. So that's why you know to put this here. And then you have off of your 6th carbon, this group, which is how you know how to put this one here. Alrighty. Now, Diels-Alder can happen on separate molecules, but it can also happen intramolecularly. And so, I guess in terms of time, I think I'm gonna let you guys think about this. Does anyone have any ideas on how an intramolecular Diels-Alder can occur? Like what part would be your diene and what part would be your dienophile? Yes, nice job, Jonathan, in the chat. So the left would be your diene. So if we had the molecule here, this is your diene, and then this is your dienophile. So just to show that they're reacting, if you were to draw the dotted lines that I always do between them, you would have this bond forming, this bond moving over, and this bond moving down. And the reason why an intramolecular can happen, because you might think, oh, this is in your S trans conformation, it can be rotated around a single bond. So even in this molecule, the single bond can rotate where it would be in its S trans and still able to interact with that dienophile, where the rest of the molecule will be attached up here, and then it would have the rest of the molecule up there. So in terms of, I'm just gonna erase that. In terms of actually making this molecule, I always count my carbons. So the first step that we did was identifying that diene and dienophile. The next part is numbering the carbons. So 1, 2, 3, 4, 5, 6. I'm going to count oxygen since it's there as a placeholder. 7, 8, 9, 10, and 11. Now, I always write on the side what's forming and what's just what's forming. Nothing is breaking actually in this. So 4 is going to go to 9 because there's a bond forming there. You're also going to have 1 forming a bond with 10, which is where our dotted lines are. And then the one thing that you might want to note is that your double bond is going to now be between 2 and 3. So if we wanted to draw this out, I always start off with my base. As in terms of like my base of like the base molecule that will be formed. So Diels-Alder forms a cyclohexene. So I'm going to just draw a cyclohexene. I know that the double bond forms between 2 and 3. So you have your molecule here, 2, 3. Now off of this, you can count the rest of your molecule. So this is 4, and then remember 4 forms a bond with 9. So this becomes 9, and 9 is connected to 10. 10 forms a bond with 1. Then you'd have 1 up there. And so then you have to draw the rest of your molecule. If you notice off of between 4 and 9, you have 1, 2, 3, 4, 5, 6. So it's 6 atoms, which also secretly forms another ring. And then you have oxygen off of it. And then the one part that you can't forget is your carbonyl group here, which comes off of carbon 9. So you know 1, 2, and then you have your group. And so that's how you do a intramolecular Diels-Alder. So just to go over our steps, the first step is identifying your diene and dienophile. For 2, you number your carbons. For 3, you form your cyclohexene ring. And for your final step, you add your other groups. Alrighty. Now, we have been talking about Diels-Alder for a while, but then there's also stereochemistry involved. For Diels-Alder stereochemistry, there are three main parts. So the first part is off of your dying. The stereochem will be maintained. So that means in terms of maintaining that stereochemistry off of your dying, that if there's matching stereochem on it, it will have matching stereochemistry in the product. So if we were to look at an example of this, I can do it for the S trans and the S cis. So I actually can do it for the S trans and then where they don't match, where one will be cis, one will be trans. So where they both match, you can have, so here, they're both trans off of here. And if you guys are a little confused about what I mean by both trans, both double bonds are trans. So that's your first double bond, it's trans. Your second double bond here is also trans. So since they're both trans, and then it can have a dienophile which attacks it. So if we were to have just substituents off of it just for practice, like here, and then don't forget heat. It would make your cyclohexene like normal with its double bond, but then your methyl groups that will come off will both be wedged because they're both trans. So if they're both trans, they're both wedged. If they're both cis, they're both wedged. And then this will also be added off. Your other groups will also be added off where you have a wedge and your carbonyl and a wedge. And then your carbonyl. And then for your other part, you can have it where off of your dying stereochemistry, where one will be S trans and then one can be cis. Wait, that was kind of drawn poorly on my part. So this is your trans. And then this is your cis. And so then when you're doing this reaction with, let's just copy it above. When you're doing this reaction, it will make it so that off of your cyclohexene that you form like normal, one methyl group will be wedged and one will be dashed. And it's just arbitrary for me when I'm choosing wedge or dash. They just need to be opposite of each other. And then you'll have your substituents coming off. And then for your next part, you can have stereochemistry on your dienophile. So if we're just using kind of your basic, that was really ugly again. If you're just using your basic diene and then you're adding on your dienophile. So if we're making something cis, where just like before we were doing this, this is cis. So then you are going to form something where it's still going to be cis to each other. Or this, I guess, does that make sense if stereochemistry, cis stays cis? Basically, they're both going to be going up or both going to be going down together. So they're both going to be wedged or both going to be dashed. So then you'll form your cyclohexene. And then you'll have both of them be wedged or both be dashed. Then you have your carbonyl, and your H. And then if we wanted to do this where it's trans, you can do something like this, where you have where the double bond here is trans. So then you add your heat, it will still form your cyclohexene like normal. And then you're going to have one be wedged and one be dashed. And I'm just, again, arbitrarily choosing which one's wedge, which one's dash. It does not really matter. And then one last part that you can have of stereochemistry is when you're looking at your bicyclic rings. So when you form a bicyclic ring, you can have something called your endoproduct and your exoproduct. And your endoproduct is going to be your more favored product. So I guess in terms of doing an example, you can have something where in order to make your bicyclic ring, you already have your diene with a ring on it, and then you have your dienophile. Let's just make it simpler, H. And then you have heat. So when you have this interaction, to draw it kind of like what we've seen before, you can have it, I'm not terribly good at drawing these, but where you have your exo, and then these will connect, and then it will be going up off of the bicyclic ring, or you can have your endo product. Which will be going down. And so that your endo product is more favored because of secondary p orbital interactions. Since it ends up going down, there are these interactions of the p orbitals that make it more favorable to have it that way. And then I think, yes. Oh. Now we are on to electrophilic addition of dienes, and then I think Kristen is taking us over, if I'm correct.
Yep. All right, let me turn on my camera. Okay, hi everyone. I'm going to be going over this in kind of breakneck speed. So just this slide, these are all the reactions you learned so far with dienes. Not all of them will matter if it's Markovnikov or not, because if you're adding like OH, for example, to both sides of the double bond, then there's no need to say it's adding on to the more substituted or whatever. So stereochem also does not always matter, but there are several that you should definitely know are anti or syn, cis or trans. So for example, like H2PDC, because you're adding the hydrogens on from a palladium plate, it has to be syn. And some notes, you have your hydrogen and a halide, you have your bromination, or any halogen can do this. You have H2PDC. One note with that is that Lindlar's catalyst can stop you at the alkene level if you're starting at an alkyne. H2O and H2SO4s are classic adding OH to the Markovnikov side. And its anti, I guess, would be BH3 or 9-BBN, which is adding OH to the less substituted side. Using a proxy acid, you can do epoxidation, Diels-Alder, as Ashley just went over. You can form a 6-membered ring or anything with a bicyclic compound. Using, yet again, a proxy acid, MCPBA plus KOH. This is where we start to be able to add OH to both sides of the double bond. So that's your anti. KMNO4 and OSO4 are your methods for using double OH addition syn. And then you guys should all know how to do ozonolysis. Easiest way is just to break the double bond and add a double bond O to both sides of the double bond. Next slide, please. All right, so a little review on kinetic versus thermodynamic control. You can tell between the two using temperature. So kinetic is formed faster, yes, but it also favors low temperature. Because these are in irreversible conditions, it will form the product faster and that'll give you your kinetic product. So I put it's usually at 0 degrees Celsius, whereas thermodynamic is I think like 78, I'm not sure. This one, thermodynamic, is your more stable product. It's formed at a higher temperature and it usually takes longer. Oh yeah, and as Maggie said in the chat, endo product is favored. Thank you. Do I have notes on that? Okay, next slide, please.
One thing to add is that sometimes if you don't know the temperature exactly, you can just put like heat for higher temperature.
Yeah, also just to read out the first bullet point, you can see the image I put, conjugated double bonds are more likely to undergo a kinetic reaction with electrophiles than non-conjugated just because they are delocalized and they're sp2 stabilized. So starting now with the reactions, you have SN2. What matters here, you can think of SN2 as they dislike bulky stuff because this is a concerted attack. So yes, it's bimolecular, hence the name 2 in SN2, but it's taking place all at once. So it's, and I told my pilot students this, but you can think about it as an umbrella. So if you go into a storm and it's like really windy, your umbrella might flip. So that's what happens to your stereochemistry. If you look at the yellow thing, you have substituents hydrogen, methyl, and Y. And they're going to be flipped. Oh, Y is what? Y is inserted. Yeah, X becomes Y. So here, your primary carbocation is favored because that's the least sterically hindered. It's okay if your leaving group is weaker, just because you want a strong nucleophile. That's the most important thing. You need the strong nucleophile to come in and create the intermediate that pushes out the leaving group. And another important note for SN2 is that the stereochemistry is inverted. So here I also put SN2, SN2, you're all good, is with a strong nucleophile such as CN, and E2, as we'll see later on, it matters more that it's a strong base such as hydroxide. Next. Yeah, so this is just a little, I put the source down below. When I was making these slides, I literally just went on Master Organic Chemistry and Chemistry Steps. I highly recommend those if you want to find practice problems or just a summary. So strong non-basic nucleophiles, they go towards SN2. But if you have a basic nucleophile, that's maybe not the strongest, it can do SN2 or E2, and we'll find out later how you can distinguish between both of them. Next, please. This is just again showing how the intermediate forms and how you create inverted stereochemistry. So it's the mechanism and showing a wedge to a dash. Oh, you can do the next slide. Yeah. I think, Jose, are you doing SN1?
Yeah.
Okay.
Hello, guys. I'm Jose, and I'll take over for SN1, E2, and solvent effects. So, could you hear me, by the way? Do I sound weird?
Yeah, we can hear you.
Good. Perfect. All right. Could I share the screen to like annotate? That's fine.
Yeah, I can stop.
Cool. All right, so for SN1, kind of like the way to look at it is there's a rate determining step being that of the carbocation intermediate formation. And if you look at the nature of the reaction, the name kind of gives it off. It's a unimolecular substitution, so it involves one molecule at a time. So kind of like to think of it mathematically, you could see it like this. And this is kind of the only thing, this is kind of the only thing that is determining the rate of the reaction. So anything that will affect SN1 has to do with this rate determining step being the carbocation intermediate formation. And some factors that affect that are the leaving group ability, the degree of carbon. So as stated previously, tertiary, secondary, these types of carbons handle better stabilized carbocations than a primary or a methyl. The solvent also helps, primarily being polar protic, And yeah, these are also factors that favor the SM1 mechanism. Also being a weak nucleophile, generally neutral. That's kind of like what the giveaway for what you want to see that tailors towards SM1 mechanism. And the product is always going to be a mix of inversion and retention, which is just another word for a racemic mixture, due to the carbocation nature of the reaction. So we can see that here with the mechanism. So the H2O, well, first the Br will leave, forming a carbocation. Then the H2O will come in, its long pair, attach. So then you get this OH2 positive, and then another H2O, probably in the solvent, will come in and pluck off that remaining hydrogen to turn into OH. And you'd be left with this is your product. That's essentially the SO1 mechanism. The way I like to look at it is it involves one molecule at a time, but it's a multiple step reaction. Whereas SN2 involves two molecules, but it happens in one reaction. It's kind of a little opposite stuff going on there. So for E2, looking at it, the rate determining step is determined by the leaving group and the base. So if you were to write that, it would be leaving group. And we could just say base / nucleophile. And the factors that affect it would be the strength of the base. You'd want a stronger base. However, you don't want like a really good nucleophile as well, because that could also favor for SN2. So probably your best bets would be KOT, potassium terbutoxide, because it's a charged bulky base. So it's strong, it's very basic, but it's too bulky to really form a substitution reaction. So those are kind of the reagents you're looking for that kind of hint towards an E2 mechanism. Furthermore, ability of the leaving group. So you want a good leaving group, and sterics. So kind of going more into that, you want the orientation to be anti-periplanar. So if this is a carbon with a leaving group here on the wedge side, you'd also want your hydrogen to be on the opposite plane. So when the leaving group leaves, your base can come in and attack that hydrogen, forming that double bond. This all happens concertedly. So like referring back to that SN2, SN1, E2 is kind of the same way. Two molecules are involved, it's one concerted reaction. So your leaving group is leaving while your base is taking away that proton to create that double bond on the molecule. And this is favored with as well with a polar aprotic solvent. And I'll go into that with solvent effects. But first, the mechanism here. So you can kind of like also show it with the chair conformation. So we see that this BR is downward, whereas this methyl is up. This methyl is up here. So this hydrogen would be up here, and then your base would come in, strip this hydrogen. You would then force this leaving group to leave. And you'd get that as your product. In other words, it looked like this. Sorry. Okay. Yeah. Stop sharing.
Kristen, do you want me to share for you again? Because are you doing E1?
Oh, yes. I can actually, would you mind sharing, please?
Yeah, I can.
Okay, thank you. All right, so for E1, completely different from E2, but it kind of does resemble SN1 in that the leaving group leaves first. And I highlighted some differences between E1 and E1CB, which we'll see on the next slide. So E1 forms a stable carbocation immediate. Same deal with SN1. Your tertiary carbocation is most preferred. And you want a good leaving group. Wait, sorry, I'm gonna tell my roommate to hold on one second. All right, might be. Okay, so you form a carbocation intermediate with a good leaving group, and you want an ionizing solvent that's protic. So similar to SN1, you favor a protic solvent. Also similar to SN1, it's not stereo specific, so you don't need an anti-periplanar hydrogen like you would with E2. And I'll go over, I have a note on like protic and aprotic solvents after this, but next slide, please. So contrasted with E1, E1CB just means using a conjugate base. So you're in basic conditions, and opposite from E1, you're now forming a carbanion intermediate, and you have a poor leaving group as opposed to a good leaving group. So these steps, it is still deprotonation, but it's not your leaving group leaving first. It's just the carbanion intermediate being formed before the elimination process occurs. So I just copied these images from this website, Master Organic Chemistry. It's a really good website. It explains E1CB really well, and it was a really good refresher for me. So I'd recommend looking at it, but it explains the two steps really well. Yeah, so in this, oh yeah, you can switch the slide. Thank you. So just as a little cheat sheet, it's very disorganized, but on the top right, if you're starting with your nucleophile or base, you can ask yourself, is it weak or strong? And that determines if it's bimolecular or unimolecular. And then the bottom right corner is just E1 versus E2. So as Jose went over with E2, it's bimolecular, there's no big barrier. It does require a strong base, and you need stereochemistry. You need it to be anti-periplanar. Whereas for E1, it's still tertiary, carbocations preferred. You don't need a strong base, and there's no stereochem. Just a note, so SN2, I didn't talk about this when I went over the SN2 slide, but SN2 prefers an aprotic solvent. I know there's also a slide after this for that. And that's because if you have a protic solvent, there's like, think of a cage of protic molecules just floating around. That decreases the nucleophilicity. So because of that, SN2 is less likely to happen, because remember, for SN2, you would prefer a strong nucleophile that can push out the leaving group when it's forming the intermediate. So SN2 prefers aprotic, SN1 prefers protic. And it's all about hindrance. Like we know SN2 hates bulky bases. Taking away that solvent cage is just taking away hindrance. Next slide, please. Okay, so nucleophilicity and basicity, they're not the same, but I know we kind of use them interchangeably, like, oh, this thing is a great nucleophile, so it's going to act on this reaction, but it's also a good base. So just to clear that up, nucleophilicity considers the reactivity of an electron-rich species. So that's our electron donating group. And this is just saying it's concerning if it bonds to any other atom other than hydrogen. So such as carbon, you see with CN, but basicity, it's strictly measuring its ratio with protons, so an equilibrium. So this is strictly if they bond to a hydrogen, such as sodium hydroxide. As a note, as a rule of thumb, a good base usually is a good nucleophile, but not always the other way around. And then looking at some trends, it's good to know. I wouldn't say it's like very, very important, but there were questions, right, where you had to compare fluoride versus iodide. So just to clear that up, both increase leftwards. Your nucleophilicity increases downwards, but basicity increases upwards. And that's it for me.
So I'll screen share real quickly to kind of draw and show the different ways the solvent could affect SN1 and E2, anyone.
Wait, Jose, did you want to screen share or are you not drawing anything?
I'm gonna screen share, it's just my iPad is
Okay,
disconnecting. It's
perfect.
being weird.
Thank you.
Okay, should work now. So to quickly show why polar product solvents favor E1 and SN1 and polar aproduct favor E2 and SN2. So if you were to put a good nucleophile that would favor an SN2 reaction like NaOH, you'd have this molecule. Great nucleophile, also very basic. However, this strong negative charge will be sequestered by, sorry, drew that wrong, by all of the surrounding water molecules that form around it. And it kind of traps it and makes it weaker because in like, if you were to view it from like a macroscopic perspective, it would be carrying all this weight to then substitute into its target, and it just wouldn't do that. It'd be so bulky carrying all this water. So in turn, it'd make it a poor nucleophile. So yeah.
All right.
Did it disconnect?
Yeah, it did. Oh, I thought you were done. I'm so sorry.
No, no, I think I'm just having connection issues. I apologize. Let me try this again. Is it working or just black screen?
I just see a black screen.
Wonderful. All right. Okay. I'll just stop screen sharing. Actually, would it be cool if I could just kind of direct you on what to draw?
Here, wait, I can try presenting it on my computer and you can annotate off of it if you want to do that.
Sure. Yeah, whatever works.
Let me try. 1 second. Are you guys able to see the screen?
Yep.
Perfect. Jose, are you able to try annotating?
I'm trying to see. Okay. So let me see if that works. Yeah. All right.
Perfect.
I apologize for the terrible drawings in advance, but yeah. So this would be the product kind of hindering in a nutshell the nucleophile. However, E1 and SN1 reactions are determined by carbocations, and the further you stabilize them, the better you kind of reduce the energetic barrier to allow the reactions to proceed forward. So polar product solvents on top of weak nucleophiles make a perfect combination because this will stabilize the carbocation enough for the weak nucleophile that isn't affected by polar products, since it's likely neutral and not charged, to either eliminate as a weak base or substitute as a weak nucleophile. However, for product, something like, I don't know, just draw a general molecule like this. This would actually promote SN2 and E2 reactions, because what happens is that normally these charged strong nucleophile bases come in an like ionic pair. And what this solvent does is that it sequesters the cation away from the nucleophile, allowing the nucleophile to attack its target. That's a terrible job. But yeah. And this is sort of the general picture on how aprotic solvents favor SN2 and E2, because the solvent only stops the positively charged species, and then negatively charged species can go ahead and do its thing. And there's no carbocation involved in SN2 or E2, so the solvent won't get in the way of the target as well. And that's how solvents do their things. If you move on to the next slide, would it just carry over?
I think it does, but
Okay.
so that's
Uh,
something I wanted to ask, I guess the students here. So let me see. So our next slide was the end of what we were planning on giving to you guys, depending on timing. But if you guys want, we can try going very briefly over some of the spectroscopy stuff that you guys have done. Otherwise, we can also just send you the link to the YouTube video that's about an hour or an hour and a half long that goes a lot more in depth of spectroscopy and how to read all the different graphs. So like CNMR, HNMR, mass spec, UV and stuff like that. That was it was created by the previous head pilot leader for Orgo. And I can also send out the slides that correspond to it. So I guess if you guys can just kind of put in the chat so that we can see what the majority of people want. Like, do you want us to try to go over it briefly, or because we can also do time for Q&A to go over problems. Mhm. Are you guys able to see the chat? Because I'm kind of not able to. I'm not gonna lie. Wait, let me look at my iPad.
Someone said Q&A. Oh,
Um,
a lot of people said Q&A, both.
kind of looks like a lot of people want both like a brief overview now and also the video.
Okay.
So I can try and do spectroscopy kind of like quickly. It's going to be more of an overview. A lot of it is taken from your textbook. So I'll just sort of go through the 4 different spectroscopy techniques. Yeah, and then we can do some Q&A and synthesis.
Do you want me to keep sharing, Maggie, or did you want to?
You can share. I'm not going to annotate.
Okay. There we go.
Okay, so for mass spec, this is the most useful for determining molecular mass and the formula of a compound and sometimes the structural features. So how it works is you basically send molecules through this vaporizer and it fragments the molecule. And depending on how easily certain bonds are broken, the molecule gets fragmented into different fragments and at different rates. And so then these are also ionized and they're sent through a magnetic field or an electric field. And the lightest ions are deflected the most, whereas the heavier ions are deflected less, and a computer receives the molecule fragments and sort of calculates a mass spectroscopy result for you. So over here on the bottom right, I have an example from your textbook of what a mass spectroscopy graph looks like. So from left to right is the mass to charge ratio. And since the electron beam ionizes every fragment to a +1 charge, M/Z ratio is basically just the mass of each fragment. And so the MZ value depends on how large each fragment is and the intensity of each peak, so how high they go, depend on how stable each fragment is. And so different functional groups have characteristic fragmentation patterns. So you can read more about it in your textbook. I won't go into too much detail here about different characteristic patterns, like ketones have specific ones that happen. And from there, you can identify which functional groups and also the molecular mass and formula of the compound. There's also some details about isotopes and how they have split peaks, but you can read more about that later. Next slide, please. So the next type of spectroscopy is UV-Vis spectroscopy. So UV stands for ultraviolet and Vis stands for visible light. So UV light and visible light are in the exact right frequency or wavelength to cause an electronic transition in the molecule. What this means is that it promotes an electron from its current molecular orbital to one of a higher energy. Specifically, they have enough energy for a pi to pi star orbital. So that's why UV-Vis is only useful for compounds that have pi bonds, specifically compounds with conjugation. And so the higher the wavelength of the peak absorbance, the less energy was needed to excite the electron. So this tells us information about conjugation, because the more conjugated a molecule is, the higher the HOMO and then the lower the LUMO. So less energy is needed to promote the electron. This is not super useful for things like structural determination in the way that like NMR is, but it's useful for things like measuring reaction rates and figuring out nucleotide compositions.
Maggie, are you muted?
Can we go to the next slide?
Oh.
So the next type of spectroscopy is infrared. So how this works is bonds can stretch and or bend. And infrared light happens to be in the perfect range of frequencies that correspond to natural frequencies that cause stretching and bending within bonds. And each bond has characteristic stretching and bending frequencies. Depending on the frequency, you can sort of tell what type of bond has been stretched or bent. So in an infrared spectroscopy, the wave number, so from left to right of where the peak appears, that is determined by what type of bond was stretched or bent. The intensity of each peak is determined by the polarity of the bond. So the more polar the bond, the greater the change in the bond length when you stretch it. So that's why the peak is more intense if the bond is more polar. Another thing to know is that stronger bonds and lighter atoms give absorption bands at higher frequencies. And resonance and hydrogen bonding also affect the position and shape of the bands. So resonance kind of changes the signal and makes it a little broader because, sorry, it doesn't make it broader. It shifts it a little more to the right to a lower wave number because resonance changes the double bond character of a bond. And hydrogen bonding makes bands more broad because hydrogen bonding occurs at different strengths. So that's why they absorb different infrared frequencies. So the thing to know about infrared spectra is mostly that they're most useful for determining functional groups because they can get really complicated because all the bonds can stretch and bend in different ways. So really the most useful thing is looking for functional groups. Some characteristic ones are like a sharp peak around 1700 is for carbonyl groups. A broad peak around 3400 is for carboxylic acids or alcohols. So knowing that is more useful than trying to figure out the entire structure from infrared. Next slide. Okay, so the last one is NMR. This stands for nuclear magnetic resonance. So the theory behind it is that nuclei that have an odd number of protons or neutrons have a property called spin. You guys have been introduced to this in terms of how electrons have two spin states. And so as the nuclei spin, they produce a magnetic field. This is more of a physics thing. And when an external magnetic field is applied to the nuclei, they can either align with or against the magnetic field. And there's a difference in energy between the state of being aligned and the state of being against the magnetic field. So it's a lower energy if you're aligned with the magnetic field and a higher energy if you're against. So what NMR measures is how much energy is required to flip the nuclei from being aligned with the magnetic field to being aligned against it. And this energy difference is determined by the local magnetic field, aka the magnetic field that's produced by local electrons. So this should sound more familiar to you guys. The electrons shield protons from external magnetic fields. So the more electron density there is around a proton, the less energy is needed to flip their spin, which makes them more upfield. Next slide. So how this actually plays out when you're reading an NMR is what determines how downfield or upfield, aka to the left or right on the spectrum, is how de-shielded a proton is. So the closer it is to an electronegative element, so something that's pulling away electron density, will make it more downfield. And if it's farther away from an electronegative element, so it's being shielded by electrons, it'll be more to the right on your spectrum, so more upfield. You also get your computer, the NMR computer calculates the integration of your peaks. So this is how high the peaks go. This tells you how many relative protons there are in each environment. So the more intense a peak, the more protons produce that signal. The last bit thing is splitting. So this is a pretty complex topic, but basically it tells you information about adjacent carbons protons. This usually follows the N+1 rule. So if a group of protons is split by, let's say, a group of 2 protons on an adjacent carbon, then you use the N+1 rule, and the peak will be split into a triplet because 2 + 1 is 3, so it gets split into 3 peaks. Multiplets can form. So multiplets are peaks that are more complex than just a regular like quartet, quintet, things like that. They can form when a signal is split by multiple environments, but the actual number of peaks that you see in an NMR depends on the overlap. So alkanes usually have the same coupling constant, which means that you can use the N+1 rule for multiplets, even though technically they would be more complex than the regular N+1 rule. Next slide. So the last thing is 13 carbon NMR. This works essentially the same as the H1 NMR. It's just that instead of different proton environments, the different peaks are from different carbon environments. As a note, we have to use 13C instead of 12 carbon, which is, even though 12 is the most common isotope of carbon, because we need an odd number of protons for spin to exist in the nuclei. An advantage of using 13C NMR over proton NMR is that 13C chemical shifts have a much larger range than proton NMR, which makes the different signals easier to distinguish. There's also usually no splitting because of the way that spectra are recorded. There's a special type of 13C NMR that does have splitting, but I won't go into detail. But yeah, so that's pretty much it for spectroscopy. I went through that really fast, so should have time for some Q&A now.
Alrighty, yeah. So I guess just to wrap up of the recording, thank you guys all for attending, or I guess watching this for the Zoom recording, and then good luck on your exam. And we also wanted just to take this moment to say thank you all for being great pilot students. We really did enjoy having all of you in our sessions, and I know many of the leaders always talked about you guys during leader meetings of their kids doing fun things or getting to know them. And so we just wanted to say thank you all. And so I think I'm going to just end the recording just in terms of time. Oh, Liam, I see your question. Sorry, I didn't see it when I was screen sharing. Yes, there will be a link to the in-depth video given when I send everyone the link to the recording, as well as a PDF of the notes that we have from this from the PowerPoint. Sorry, words are hard. So yeah, I think that's about it. I'm gonna end the recording and then we can do Q&A.